Congratulations, first of all, to Nikolai. It's wonderful to reach an age by 80. It was 80 years. This is wonderful if one can survive so far. Now, I have worked with Nikolai for a long time, say about 20 years, since 1969. How did it all start? Actually, we first met in Australia at an IAU colloquium in Port Douglas, which is a very nice place at the Great Barrier Reef. Unfortunately, neither Nikolai nor myself had the opportunity to really dive down into these waters, which I did later with my wife, which was very wonderful. But the environment was very good. And so, of course, we knew each other already by that time from the literature. Nikolai had produced a lot of wonderful papers, especially about accretion disk and accretion onto neutron stars. Now, I like to point out this one here. Note the enormous amounts of citations there on the black hole binary paper. Myself, I had concerned myself with observing X-ray binaries, first with balloon experiments, and then moving to satellites. First, actually, was the Mir Hexe, which we did together with Rashid Sunyaev on the Soviet space station. And our early achievement in the mid-70s was to discover the cyclotron line in Hercules X1, which, as you had mentioned, Galina, is the first direct measurement of a magnetic field in a neutron star. So, meeting in Port Douglas, we of course talked about Hercules X1 because we both were interested in this object. And so we agreed to work together and combine our forces, especially good because in Moscow, there were a lot of capabilities in theoretical studies, which I missed. Theoretical studies and modeling, which I actually had not done so far. But I had a good experience in data analysis and had made a lot of observations and data analysis. So thank you for saying that we produced 30 papers together. Maybe that's true, but the ADS just lists 25 common publications where both names, Shakura and Staubert, are on the author list. Apart from that, we did projects, actually wrote proposals to the Deutsche Forschungsgemeinschaft, DFG, and the RFBR in Russia, and received corresponding grants, which enabled us to travel and to visit each other. So we had several nice visits to Moscow and to Tübingen, of course. And importantly, we became good friends doing all of this together. So the collaboration, let me introduce the key people. Nikolai Shakura, of course, in Moscow, and Konstantin Postnov. They are both here in the Sternberg office there, which appears that there's a lot of work going on. And Dmitry Kolesnikov, which actually I did not meet in person so far. but we know, of course, each other from the literature and from other interactions and having common papers. Now, from Tübingen, it was myself and Jörn Wilms and Dima Klotchkov. Dima Klotchkov actually was a student of Nikolai's and made his physics diploma in Moscow. And one of these visits to Moscow, I got to know him, and I kind of suggested whether I could import him to Germany, whether he would like to come to Tübingen and do his PhD work with me, which finally happened. So it's Jörn Wilms here and Dima Klotchkov. Can you see this? Actually, it's blocked here in my screen. Can you see Dima?
Yes.
Yes, we can.
Yes, you can. Good. So our common science interest, of course, is X-ray binaries and very specifically Hercules X1. And these is a list of things we sort of investigated. The accretion disk and its column, the 35-day modulation, I will come to it, what it is, neutron star free precession. Actually, this is the main topic. Pulse profiles, variability, pulse period, evolution, and so on. But I do have to say that the first point, X-ray spectral cyclotron lines, we actually did nothing really together. I was not able actually really to interest Nikolai and Konstantin to go into the deep physics of the cyclotron line production on neutron stars and magnetic fields. Anyway, the other topics all boiled down to one question, namely, what does the neutron star do? Possibly, does it do free precession? So just to introduce X-ray binaries, you all know this very well. I do this very fast. So we have a binary here, and the neutron star is accreting from the optical companion, and the matter falls down along the accretion. The accretion follows the magnetic field lines, and the material is just stopped at the polar surface of the neutron star, and it gets very hot, so we get X-rays, and there's a beam emitted, probably in the pencil beam and also in the fan beam direction. Now, what are the critical observations on Hercules X1? For instance, what we do find, and we know from the early discoveries by Uhuru, that there is a long-term flux modulation on this side here. Actually, it's a 35-day modulation with the main on, as we call it, and a short on. There are binary eclipses with 1.7 days. There's pulsation because the magnetic axis and the spin axis of the neutron stars are not aligned, so we get a lighthouse effect there with 1.24 seconds. It turns out that the pulsation has a good pulse profile there, but this pulse profile is not constant. It is variable, and particularly variable with the 35-day phase. The other thing is the period of pulsation itself, 1.24 seconds. We find that it's variable. This is a plot here showing the 1.24 seconds as a function of time, and there is a general spin-up trend, but there are deviations here with periods of short spin down and over again. And so there is spin up and spin down change back and forth. And the important thing is this 35-day clock. The onset of the flux we call the turn on. In principle, we have sort of a 35-day clock, but this clock is very irregular. It is not very steady. So the turn on happens, there are deviations from a pure, strong clock, and this is displayed in this plot, the so-called O-C diagram, which means the observed minus calculated turn-on times, where we assume a constant period C, calculating this by a period of, it turns out, 20.5 binary periods, which is in days 34.85 days. And this shows here how variable this is. So it's a quite irregular clock. Okay, and this is supposed to show how the radiation receives the Earth and also its companion, H3 Hercules, because there is an accretion disk which apparently is warped and precesses. And the precession of the accretion disk sort of blocks the X-ray beam regularly, such that we get the 35-day flux modulation. But what about the neutron star itself? Now, the big question for all work we had together is, does the neutron star show free precession? Now, then there was a very important observation by Trumper et al. Using exosat observations of Hercules X1, and they found that indeed these pulse profiles are systematically variable. They change their shape with 35-day phase. So since we think that the X-rays which produce the pulse profiles emanate from the neutron star's surface, it was natural to assume that these variations might have to do with the neutron star itself, especially free precession. Now, there was a nice paper in 1977 where Shaham actually made this proposal specifically with application to Hercules X1. Okay, I will not spend much time on this picture. You all know what precession is of neutron star, but the important point is that we have an offline sort of magnetic dipole field with the North Pole and the South Pole, and there is an offset from the straight line here to the North Pole. And with precession, the X-ray emitting pole moves around like this. So we should expect that while this is moving, the radiation pattern changes and produces the changes in pulse profile. Okay, I like to go to very briefly to 4 important papers. Does the neutron star show precession? In all those 4 papers, the answer is yes. And one is I will go through this from Prof, Shakura, Kolesnikov, and myself. So let's start neutron star free precession paper 1 from Prof. We actually, on this, we used pulse profiles observed with the Russian X-ray timing explorer, the United States satellite, and the pulse profiles are shown here. And you can see they change their shape with 35-day phase, which is listed here on the right-hand side of the plot. So the procedure is, of course, observe pulse profiles, which actually I did mostly by proposing for RxTE observations and got all this. Konstantin and Nikolai produced a model, assuming certain model parameters in order to predict how pulse profiles should look like. And of course, the idea is to compare the observed pulse profiles with the predicted profiles from the model. Now, I cannot go into very much detail on the models or so, and there are plenty plots like this here in the Postnov et al. Paper, comparing the observed profiles, which are hard to see, which are in black, and the predicted profiles from the model, which are in magenta. And it turns out it's a very, very good fit. And this fit requires the free precession. So the neutron star free precession is okay. And more so, we have to conclude that possibly neutron star precession is the prime 35-day clock, 35 days, and apparently the neutron star accretion, the accretion disk in its precession takes up the same period, and the idea is that magnetic interaction of the inner disk of the neutron star with the magnetic field of the neutron star is responsible for slaving the disk to the same precessional period as the neutron star. Neutron star free precession paper 2 from Nikolai Shakura. He made efforts to do optical observations and somehow managed to separate the contribution on optical light, which comes from the accretion disk. And doing so, again, one can model what to expect from this processing accretion disk, and compare to observations. Again, this is a selection of a few profiles, 35-day profiles for different observations. And no, this is, yeah, binary profiles, sorry, for different phases of 35-day phase, which are shown here. So this is the 35-day phase. And again, the conclusion is the model predicted flux fit very well what is observed. And so we assume that the neutron star undergoes free precession. And the variability can be explained by forced precession of the accretion disk through the magnetic interaction. Paper 3. by Dmitry Kolesnikov and others. I'm not involved actually on this paper here, interesting. It analyzes the pulse period evolution itself. Now, this is not pulse period, but frequency. But what one can see is that there is a spin-up, a general trend for spin-up, and then a lot of local variations. And the question is, that is answered here in this paper, in this, is this possibly a sign of free precession of the neutron star? And again, a model was produced to predict these variations in pulse period or pulse frequency. And again, this is a selection, one plot of lots of plots from this paper where one compares the model and the observations, and it appears there's a very good fit. And actually always, as always, from those fits, if they work, one can extract the model parameters about the system. Otherwise, and of course, has been done to optimize these parameters to make the best fit to the data possible. Paper 4, neutron star free precession by myself, basically. Again, using the pulse profiles and the change of the pulse profiles with 35-day phase. I had produced a database, actually a template of pulse profiles, typical pulse profiles for every small interval, actually a hundredth of the 35-day phase with the characteristic pulse profile. This is from a selection of data of two 35-day main ons used by, observed by RxTE. So taking all other observations RxTE, one can then find from these pulse profiles a turn-on of the 35-day by taking those profiles, determining their time, their 35-day phase, because the profile shape is very characteristic, and one can find the 35-day phase from this. Now, if one can then extrapolate back down to 35-day phase 0 and get a value at time in MGD for the actual turn-on. Now, those turn-ons produced from pulse profiles are shown in the O-C diagram with red points here. The green points are the long-term history of O-C turn-ons observed from the accretion disk itself. That means from the modulation, 35-day modulation observed. So the conclusion, there is only one 35-day clock. Apparently, the pulse profile clock, which we think is associated with the neutron star itself, and the flux modulation of 35-day, which we think is associated with the precession by the accretion disk, is actually identical, which requires that there is a physical interaction and connection between the neutron star itself and the accretion disk. And the idea is that the neutron star precession is the prime clock. So I think from this point, the question is answered. Yes, there is free precession. I like to mention that a recent support has been found to this idea by observing polarization by the satellite XP, IXPE, United States satellite, and the paper is published in Astronomy Nature by Heil et al. And they strongly endorse this idea by interpreting their data from polarization, which is a new, relatively new, since 2 years, way of observing X-ray objects. So, to my mind, there are then two questions really to be answered. How does the magnetic interaction between neutron star and disk work? Maybe I have missed it, but to my knowledge, there is no hard treatment there, how this in principle, in detail, actually work. And so I'd like to encourage Nikolai and Konstantin and co-workers to get to this problem and solve it and describe in detail how this might work. The other question in my mind is, maybe you can answer this straight away, but there is one observation which I have not mentioned here, which has been done during a so-called anomalous low, where we find that the precessional period of the accretion disk must have been very, very low. The period must have changed from 34.8 period, which is the usual period, to something like 33.5 days. Now, my question is, if there really is a rigid connection between precession period between the neutron star precession and the accretion disk precession, this requires that the neutron star precession is actually able, as the neutron star actually is able to change its precessional period by about 3.7% in very short time scales. Very short means over a few 35-day cycles. I had published a paper in 2024. This is wrong. This is wrong. This is in 2009, actually. Sorry about this. Claiming that there are two clocks just by observing these data from the anomalous low, which showed that either the accretion disk had done an extra cycle of precession by having this short period for a period of 600 days or so, or the neutron star itself also changed its precessional period to a very low value, namely 33.5 days or so. My general, I mean, my gut feeling is that the neutron star should not be able to do that because of its big mass and everything, but maybe this is wrong. So please let me know what you think about this, and I will revisit my early paper on this, whether I made any mistakes in there, maybe in interpretation. So that's it. And I like to say to Nikolai, take care, all the best for the future, and stay active. And hopefully we can continue to work together and to cooperate again. So cheers. All the best to you, Nikolai. Thank you.
Oh, thank you, Professor Staubert. This is an ultimate review of Hercules X1 facility. Nikolai,
Thank you, Rüdiger.
Thank you. So I may say, I do have a few more pictures to show from visits.
Yes, please.
Back and forth. Should I do this?
Yes,
Okay.
absolutely. Please.
Okay. So here's Nikolai and Natasha in their home for one of our visits to Moscow from Tübingen. Of course, this is Dmitry Klochkov, also, it's Natasha.
Yes.
And we have a corresponding visit of Nikolai and family. Natasha was also there, and Konstantin. This is in my home. Actually, this must have been, I don't know, in 2000 something.
2007, something like that.
2007 or something, yeah. Wonderful, and Konstantin has one of its daughters here, right there. And this is actually more recently, it's only 6 years ago, in Tübingen at the festivities to my 80th birthday, together with Joachim Trümper, and Nikolai had just sort of presented a gift to me, one of his books. Again, from the 2019 visit in Tübingen, where we had a small meeting on the occasion of my 80th birthday. Nikolai with myself on the back, and Natasha with myself on the back. And this is a very nice picture I like very much from the evening party we had then with Nikolai Shakura first, Rashid Sunyayev, Joachim Trümper here, my PhD advisor, by the way, and long-term collaborator and friend, and Günther Hasinger, who also was a very important student of Joachim Trümper. So thank you very much. This was it.